Organic compounds. So early chemists observed that some chemicals come from living things and some come from non-living things. And so the chemicals that came from living organisms, plants, animals, etc., were called organic compounds. And those that came from rocks and water and things like that were called inorganic. They found that the organic compounds were more easily decomposed. You could burn them, it was pretty easy to destroy them. But they were very difficult to make in the lab. And inorganic was kind of the opposite. It was pretty easy to make them, but it was more difficult to decompose them. So today, we have learned how to make organic compounds in the lab. And this is a big deal. This is actually one of the things that my oldest two kids are doing in their graduate work, is they're synthesizing organic compounds. So they're looking for a pheromone for a fruit fly. Well, you can't just go to the store and buy the pheromone that this one weird fruit fly uses, right? Nobody makes it. So you analyze the pheromone, you find out what its structure is, and then you figure out a way to make it in the lab. And then that makes an excellent attractant for a fruit fly trap, right? So that's organic synthetic chemistry with a practical application to agriculture. It's kind of neat. And that reduces the amount of pesticides and things that would have to be sprayed to kill the fruit flies, because now you're using a natural component to attract them to sticky traps. And so it's just a win-win all around. Organic compounds are composed of carbon and hydrogen. If it doesn't have carbon in it, it can't be an organic compound. Other elements that are often in organic compounds, oxygen, nitrogen, phosphorus, and sulfur, there may be trace amounts of other elements, but it's mostly carbon and hydrogen. And we are called a carbon-based life form because most of the chemicals in your body are organic chemicals, and they have carbon as their main component. So carbon is the key. Here's a structural formula for methane and a space-filling model. Methane contains carbon and hydrogen. It is an organic compound. Here we see that carbon likes to form 4 bonds. And we'll study why that is later. For now, just know carbon wants to have 4 bonds. Carbon makes covalent bonds, and it wants to make 4. It can do that through any combination of single, double, and triple bonds. It could be 1 single and 1 triple. It could be 2 doubles, etc., 4 singles. It can make these bonds with other carbon atoms or with different elements. So, it's not too picky about that. What makes the chemistry of carbon unique from other, like oxygen chemistry or something, is that carbon frequently bonds to itself to make long chains, branched structures, and ring structures. And so it has a wide variety of different types of compounds. So here we see a straight chain where there's 3 carbon atoms and they form a line. And then what makes up the other 4 bonds needed are hydrogen atoms. Here is a compound with 4 carbon atoms, but instead of them being all in one line, it's branched here. And again, you make up the difference on the 4 bonds to carbon by sticking hydrogens in there. This is cyclohexane. This is where we've got 6 carbons and they're making a ring. It's like they're playing Ring Around the Rosie. We can have double bonds. Here, these carbons each have 4 bonds, 2 single bonds, and then the double bond is 2 bonds, so 4 bonds. Here we have a triple bond between carbon atoms. Here we have an example of carbon making a double bond with oxygen, a single bond with another oxygen, and a single bond with this carbon. So again, 4 bonds. This is an introduction to organic compounds. I want you to just kind of have an idea of what they're like. So after Chem 1A, you'll take Chem 1B, and then you'll take the 2-semester organic sequence, and then you'll learn a lot about these guys. We divide organic compounds into 2 broad categories. So compounds in general can be inorganic or organic, and then organic compounds can be hydrocarbons or functionalized hydrocarbons, special hydrocarbons. So hydrocarbon contains carbon and hydrogen, hence the name hydrocarbon, hydrogen carbon. These are common fuels. So oils, gasolines, liquid propane, natural gas, these are all hydrocarbons. They burn very nicely, so really useful things. In the hydrocarbons, we can divide those into categories based on the kinds of bonds that they have. If they only have single bonds, they're called alkanes. If they have double bonds, at least one double bond, it's called an alkene. And an alkyne is something that has at least one triple bond in it. The double and the triple bonds affect the chemistry of that compound, and so they are significant. When we name hydrocarbons, there is a base name, and that is determined by the number of carbon atoms. And then the suffix that we put on there tells us what kind of bonds are present. So the base name, the first four are weird. The others are very much like those prefixes we needed for the molecular compounds. So instead of penta for 5, it's pent. We just leave off the A. And we've got hex, hept, oct, non, and dec. So those are the same numbers as they were before. The weird thing is the first 3. It's not mono, di, tri, and tetra. It's meth, eth, prop, and bute. So how do you remember that? So the way I remember it is a silly sentence: Mom eats pickled bananas. So Mom eats pickled bananas. I'm not sure if you can actually pickle bananas, and it doesn't sound like those would be good, but you know, it helps me remember. So methyl, ethyl, propyl, butyl. Methane, ethane, propane, butane, meth, eth, prop, bute. The order, 1, 2, 3, 4. So this prefix means that there's one carbon. And then we put a suffix on it, ane, ene, or ine, depending on whether it's only single bonds, has at least one double bond, or has at least one triple bond. So we can have octane, would have 8 carbons and only single bonds. We could have hexyne, 6 carbons with at least one triple bond. These are some examples of common hydrocarbons and what they're used for. A lot of these are things that we would burn. But this one, ethene, is a ripening agent in fruit. And fruit does give that off naturally, but you can also add it to the environment and cause the fruit to ripen more quickly. So these all end in ane. And when we look at their structural formulas, we see they only have single bonds. Ethene, eth is a prefix that means 2 carbons, and ene is the suffix that means a double bond. So this is 2 carbons with a double bond. Ethyne has a triple bond, so 2 carbons with a triple bond. Any questions? Yeah?
Are all organic compounds found in nature naturally?
No, all organic compounds are not found in nature naturally. So chemists use the word organic differently than it's used like at the grocery store. Right? At the grocery store, you get an organic apple. It hasn't been sprayed with unnatural pesticides, right? But actually, all apples are organic because they contain carbon and hydrogen compounds, right? Cellulose and glucose and all of these different things. So there are a lot of naturally occurring organic compounds, but then there are others that we have made. And some of them for practical purposes and some just to see if we could. Anybody else have any questions? So those are the hydrocarbons. A functionalized hydrocarbon has a special group on it. It's either a particular atom, maybe it's got an oxygen, or it's got a group of atoms, or we could even consider multiple bonds to be a functional group. It's called a functional group because that group changes the functionality of the molecule. It'll give it different chemical and physical properties. So we put these into groups. So we look at, oh, okay, we have alcohols. They all have an OH functional group on them. So those are in a category of alcohols. And then you can have another category for each different functional group. So when it really gets kind of complicated is when you have a compound that has lots of different functional groups on it. So things can get complicated pretty quickly. But here in Chem 1A, we can just keep it simple. So that's nice. So here are two members of the alcohol family, methanol and isopropanol. So here, meth means one carbon. So we have meth, and then the prefix "ol" means it's an alcohol, so it has this OH group. I'm explaining that to you, but I'm not going to require you to name or write formulas for alcohols. Here, isopropanol. So prop means three. So this has 3 carbons. The iso prefix has to do with telling us that they are not, well, anyway, it's complicated. But again, we have this OH group. So both of these are in the alcohol family because they have the functional group OH on them. So these are the main families: alcohols, ethers, aldehydes, ketones, carboxylic acids, esters, and amines. I'm not going to test you on whether you can recognize what kind of a compound it is, but I want you to be aware of this. These problems could show up in homework assignments or a worksheet or something, but I wouldn't ask you, I wouldn't give you this formula on a test and say, what family does it belong to? Okay, because that's really more of an organic chemistry question. I just want you to be aware that this exists, okay? So we see these functional groups. Here's the OH. This functional group is the O between 2 carbon things. R just stands for a hydrocarbon, some numbers of carbons and hydrogens. So in this example, for R, we could put CH3CH2. So that's the R. There's an O in the middle, and it's bonded to another carbon. So it matters that this oxygen is between 2 carbons, whereas this oxygen is between a hydrogen and a carbon. That's different. Here we've got a carbon double bonded to oxygen. On that carbon, there's a hydrogen on one side and a carbon on the other. Here, this one has a carbon on both sides, and so that makes it a little bit different. Okay, so this first one is one we should be able to do. Draw the structural formula for nonane. There are branched versions of nonane, but we're just going to do straight chain things. So nonane has how many carbons in it? 9. The prefix non means 9. It's kind of like the word 9, isn't it? So we need to put 9 carbons on here. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the sort of math you do in organic chemistry. It's a lot of counting, usually not much higher than 10. So you have to count carbons. What else is in this compound? Hydrogens. The nonane, ane tells us that all of these are single bonds, but now all of those carbons need to have 4 bonds. Everything's single bonds, so we'll just put in the 4 bonds for each of the carbons. Structural formulas can be a bit tedious to draw. And then each of those single bonds where we don't have a carbon is going to have a hydrogen on it. So there needs to be a hydrogen here, and a hydrogen there, and one up here. And organic chemists have a lot of shorthand ways of doing this, because nobody has time to do this. It's just really tedious. But that's the structural formula. It's showing how everything is connected. What would the molecular formula for that be? where we just say how many carbons and how many hydrogens. Well, C9, right? We could count the hydrogens. That doesn't sound fun. Each of these carbons has a hydrogen above and a hydrogen below, right? So there's 2 for each carbon, and then there's an extra one on this end and an extra one on that end. So it's 9 times 2 plus 2, H20. But you can also count them. So that's nonene. If I asked you to draw the structural formula for nonene, you'd need a double bond. Where do you put the double bond? Well, in this class, I wouldn't care. I just want you to know that the ene means a double bond. So let's make this into nonene. We need a double bond. I'm just going to stick it in here. So if I stick the double bond in there, now those 2 carbons, this one and that one, they each have 5 bonds. So what we need to do then would be to take off a hydrogen from that carbon and a hydrogen from this carbon, so that the carbons still have 1, 2, 3, 4 bonds each. So that changes its overall molecular formula as well, so then this becomes C9H18. That's the extent of stuff that might come up on a test. Or I could give you the structural formula and ask you what its name is. If I gave you this, I would expect you to count the carbons, come up with known, and then see that there's a double bond and say that's nonene. Okay. Questions that could come up on homework and stuff, things like this. To which family does this compound belong? Wouldn't ask you that on a test. So this is the functional group right here. We've got a carbon double bonded to oxygen, and then this carbon is attached to carbons on each side. So we would go look at the table, and there's 4 of them here in the middle with the carbon-oxygen double bond. But here there's a carbon on one side, oxygen on the other side. Here, that one looks right. It's got a carbon here and a carbon on each side. This one, there's an oxygen on this side. This one, there's another weird kind of oxygen over there. So that compound that we're looking at is one of these. It's a ketone. Any questions?